Welcome to Section 2 of the Acid-Base Physiology Review. In Section 2, we will walk through how the body handles an acid load, going through both the immediate buffering response as well as the pulmonary and renal response to an acid load. Welcome to Section 2 of the Acid-Base Physiology Review. In Section 2, we will walk through how the body handles an acid load. Let's first talk about an excess of fixed acid in the setting of a metabolic acidosis. Non-volatile acids can increase the free hydrogen concentration. This can be related to lactic acidosis, ketoacidosis, or the organic anions that accumulate in the setting of situations such as renal failure. The lungs can serve as an immediate means of correcting pH by increasing minute ventilation. This increases carbon dioxide removal, which shifts the system as diagram to the left and reduces free hydrogen concentration. This is a quick response. Hyperventilation is stimulated by the chemoreceptors in the central nervous system and the chemoreceptors and the pH receptors in the carotid body. Once again, to walk through this. When there is an excess of non-volatile acid, the lungs respond by increasing minute ventilation. This will decrease the carbon dioxide concentration, driving this equation to the left. The end result is that the free hydrogen concentration will be lower and pH will move toward the normal range. The kidneys can serve to excrete acid but must conserve bicarbonate to do it. The proximal tubular cells activate carbonic anhydrase to maximize reabsorption of filtered bicarbonate. The distal nephron secretes hydrogen ions, either in the form of titratable acids or ammonium. Remember, anytime a hydrogen ion is secreted, a bicarbonate is reabsorbed. So the net effect is increased bicarbonate reabsorption with increased hydrogen ion excretion. This provides a substrate to drive the reaction system to the left. Volatile acid, however, acts differently. An increase in carbon dioxide concentration may be caused by hypoventilation. Pulmonary dysfunction is the root. The kidneys can conserve bicarbonate to provide a buffering substance for this acid. However, this compensation can take days. The degree of compensation lets us infer whether the process is acute or chronic. When compensation is inadequate, it usually suggests that this is an acute process. However, if you see an increase in bicarbonate concentration suggesting a renal response, this may suggest that the volatile acid excess has been present for some time, and this is more of a chronic respiratory acidosis. In the renal physiology section, we reviewed bicarbonate reabsorption. However, let's do it again. The maintenance of bicarbonate concentration within a given range and the net acid excretion in the kidney occurs through three primary mechanisms. First, bicarbonate, which is filtered at the glomerulus, is reabsorbed near maximally. Next, new bicarbonate is formed. New bicarbonate is formed coupled always with hydrogen secretion. Hydrogen secretion is coupled to titratable acids that are filtered in the kidney and serve as one means of increasing net acid excretion. And the final, most regulated means of increasing net excretion is through the excretion of ammonium. Ammonia is formed in response to acidosis. Ammonia serves as a means of increasing hydrogen ion excretion in the form of ammonium. Bicarbonate is freely filtered at the glomerulus in essentially the same concentration present in the blood. However, to maintain plasma bicarbonate under stress, nearly all the filtered bicarbonate is reabsorbed. This is approximately 4,300 millimoles per day of bicarbonate. The primary segment of the nephron responsible for bicarbonate reabsorption is the proximal tubule. As we walked through previously, the reabsorption of bicarbonate is indirectly coupled to the reabsorption of sodium via the activity of carbonic anhydrase and the sodium-hydrogen exchanger in the proximal tubular cell. To walk through again in more detail, filtered bicarbonate enters the tubular lumen. Hydrogen is secreted via the sodium-hydrogen exchanger present on the luminal side of the proximal tubular epithelial cell. The hydrogen couples with the bicarbonate, and with the help of carbonic anhydrase forms carbonic acid, which then dissociates into water and carbon dioxide. Both of these, not being charged, can freely diffuse into the proximal tubular epithelial cell. The reaction is then reversed, where water and carbon dioxide combine, form carbonic acid, and dissociate then into bicarbonate and a hydrogen ion. The bicarbonate is reabsorbed through a sodium bicarbonate cotransporter in the basolateral segment of the proximal tubule. The hydrogen that is formed serves to recycle the process. The hydrogen exits the cell through the sodium-hydrogen exchanger, providing another hydrogen to facilitate further bicarbonate reabsorption. In the distal tubule, the reabsorption of bicarbonate is different. Synthesis of new bicarbonate occurs primarily in the distal nephron. At this point, most, if not all, of the filtered bicarbonate has been reabsorbed. However, there are other buffers present, specifically mono and dibasic phosphate, that can serve to trap hydrogen that is secreted through channels such as the hydrogen ATPase present on the alpha intercalated cell of the collecting duct. Once again, recall that anytime a hydrogen is secreted, bicarbonate is reabsorbed. Where does this hydrogen come from? This activity is stimulated in the setting of acidosis. Acidosis then stimulates the uptake of carbon dioxide into the intracellular space. Carbon dioxide combines with water to form carbonic acid. Once again, carbonic anhydrase activity is present, which allows carbonic acid to dissociate into the free hydrogen and the bicarbonate. The hydrogen is then secreted, is coupled either with a titratable acid, such as monodibasic phosphate, or ammonia to form an excretable acid. The bicarbonate which is formed is reabsorbed through the bicarbonate chloride exchanger present on the basolateral surface of the tubular epithelial cell. This formed bicarbonate is thus added to the blood to correct an acidosis that may exist. Very little hydrogen ion is excreted freely. Most is excreted in the form of ammonium or titratable acid. Important to recall, the pH of the urine varies according to the location in the nephron. In the proximal tubule, the urine pH is close to, although still lower than blood, as the bicarbonate concentration is higher. However, as the urine moves distally, all the bicarbonate has been reabsorbed, and there is distal acid excretion, lowering the pH to as low as a pH of 4.4. Normal pH of the urine tends to be not quite this low, but between 4.5 and 5. Hydrogen ion excretion is affected by various factors as well. The amount of bicarbonate delivered from the proximal tubule, the factors enhancing sodium reabsorption also will enhance hydrogen secretion. As we stated before, aldosterone activity, creating a negative luminal potential, enhances hydrogen secretion. The acid-base status of the body has an effect on hydrogen ion excretion. Decreased intracellular pH enhances hydrogen secretion and lowers urinary pH. This is a response to an acidosis, either a metabolic or respiratory type. Hypokalemia, as we previously mentioned, also decreases intracellular pH and enhances hydrogen ion secretion. Finally, aldosterone, through direct stimulation of the hydrogen ion pump in the cortical collecting duct, as well as an increased sodium reabsorption, creating the negative lumen potential, increases hydrogen ion excretion and total net acid excretion. Ammonia plays a central role in the regulation of net acid excretion. As we stated before, the three major means of the kidney to maintain bicarbonate concentration in a given range are to 1. Reabsorb near all the filtered bicarbonate, Secondly, to excrete acid in the form of titratable acids with filtered phosphates, sulfates, and other buffers. The second process mentioned is largely unregulated and simply relies on whatever the filtered load is. However, the last component of acid excretion regulation, ammoniogenesis and ammonium excretion, is regulated. Acidosis stimulates ammoniogenesis. This occurs primarily in the proximal tubule cell. Glutamine formed in the liver is then delivered to the renal tubular epithelial cells. Depending on the acid-base status, glutamine is converted into ammonium as well as two bicarbonate molecules. The bicarbonate is reabsorbed and the ammonium is excreted in the tubular lumen. Ammonium lives in equilibration with ammonia and travels through the nephron. Ultimately, in the collecting tubule, depending on the hydrogen secreted, the amount of ammonium is regulated. If there are high hydrogen secretion rates, there is more ammonium created. Ammonium is then trapped in the tubular lumen as it is excreted. This results in net acid excretion. However, if there is not a stimulus for hydrogen secretion, then more free ammonia lives. Ammonia can then continue to be recycled throughout the tubular lumen until its use is necessary. Once again, changes in urine pH, urine flow, arterial pH, and potassium all affect ammoniogenesis. A low urine pH and acid urine increases the trapping of hydrogen to ammonia to form ammonium. Increased flow rates will also increase ammonium excretion. Both arterial pH as well as urine pH have similar effects on ammonium production as well as ammonium excretion. The net result is increased acid excretion to return pH into the normal range. Finally, serum potassium has an effect on ammonium production and excretion. Hypokalemia, by creating an intracellular alkalosis, stimulates ammoniogenesis. Ammoniogenesis then leads to ammonium production and increased net acid excretion. Hyperkalemia has the opposite effect. We've talked briefly, but to go into more detail about titratable acid, let us proceed through the following. As we said, hydrogen is secreted into the tubular lumen, but cannot be excreted as free hydrogen. Buffers trap the hydrogen into the tubular lumen so that net acid excretion increases. Phosphate is the major titratable acid in the mono and dibasic form. Other small titratable acids include creatinine, beta-hydroxybutyrate, urate, lactate, and sulfates. Titratable acid excretion is largely unregulated. It's simply dependent on the availability and the urine pH. Dietary phosphate intake can have an effect at extreme levels on the amount of titratable acid available for net acid excretion. If in the setting of extremely low intake of dietary phosphate, less titratable acid may be available for net acid excretion. Alternatively, with very high phosphate intake, we may be able to increase net acid excretion in the form of titratable acid. These two diagrams demonstrate the role of titratable acids. Once again, in the proximal tubule cell, hydrogen secretion is coupled with sodium reabsorption. The hydrogen is free in the tubular lumen, but then is trapped by the phosphate that is filtered. Similarly, in the collecting tubule, the hydrogen secreted through the hydrogen ATPase can be trapped and excreted in the form of a hydrogen diphosphate. This concludes Section 2 of the Acid-Base Physiology Review. The key points to remember from Section 2 is that the body has developed different mechanisms to handle an acid load. The most immediate effect is buffering of the acid by bone, bicarbonate, hemoglobin, and other buffers that are present in the body. The next most immediate effect is changes in minute ventilation, specifically an increase in minute ventilation to increase CO2 excretion. Finally, the kidney has the responsibility for maintaining bicarbonate concentration in the normal range over time by changes in net acid excretion and bicarbonate reabsorption. Next, we will talk about how the system handles base in Section 3.